Hello everyone, in this lecture I will discuss curvilinear coordinates. So far we discussed Cartesian coordinates. However, in many physical problems we find that to use the Cartesian coordinate it's not suitable, and in other situations it might lead to very complicated mathematical relations. Therefore, it's suitable to discuss coordinates other than Cartesian coordinates. So let's have a quick reminder of the Cartesian coordinates. So if we have an x, y, z coordinates here and a point P located in the xyz plane, and remember this is I hat and this is j hat and this is k hat. Now the point P has intercept with the z-axis at this point right here, and it has intercept between the x and y plane like this one right here. This new point here, it has intercept with the x-axis like this one, and it has intercept with y-axis like this one right here. So this one here is actually x and this one here is y. Therefore, the total differential length dl is given by this relation. So dl equal to I dx plus j hat dy plus k hat dz. Four things we are actually interested in: gradient phi, divergence A, Laplacian phi, and curl A. Now in Cartesian coordinates, gradient phi, it's I partial phi partial x, j partial phi partial y plus k hat partial phi partial z. Remember the del operator, it's I partial partial x plus j partial partial y plus k partial partial z, and phi here is a scalar quantity. In Cartesian coordinates, divergence A equal to partial ax partial x plus partial ay partial y plus partial az partial z, and divergence A, the resultant, is scalar quantity, as we can see in this one here. Now Laplacian phi in Cartesian coordinates, it's the second derivative of phi with respect to x squared plus second derivative of phi with respect to y squared plus partial to phi partial z squared. Now the curl in this one, you actually open a determinant here, this is vector, and I, j, k. Now the second row is the components of the first vector, partial partial x partial partial y partial partial z, ax, ay, az. In physics, actually we are interested in three coordinate systems, which is Cartesian, spherical, and cylindrical coordinates. Now let's discuss spherical coordinates. If this is x, y, z, now we have a point P right here. It has a position in spherical coordinates. We'll see r, theta, phi. Now r here is the position from the origin, so this is r. Now theta is the angle with the z-axis and upon intercept with this point here in the xy plane, will be somewhere here. Now the new position vector, this one right here, has an angle phi. So to represent a sphere, three coordinates we should consider here is r, theta, and phi. In Cartesian, xyz, in spherical, r, theta, and phi. If you would like to draw a sphere, you have a radius, then you make this radius sweep a circle like this one here, and this circle making angle phi, then you create like this one here, you move this one, which is theta in this case. So drawing a sphere, you need r, phi, and theta. Back to this figure here. Now let's define the unit vectors for the three new coordinates r, theta, and phi. So if this is r, so the unit vector r hat is directed this way. So this is r hat. Again, when you draw back to this one here, when you draw a sphere, you actually making angle theta. So this theta directed this way right here, so it will be this one theta. And when you create a sphere, you first draw a disk and create an angle phi. So phi in this case will be this way. So this is phi hat and this is theta hat. A vector in spherical coordinate system is defined generally by A equal to r hat A r, which is related to r theta phi, plus theta hat A theta r theta phi, plus phi hat A phi r theta and phi. Like Cartesian coordinates, I hat cross j hat will give you k hat. Similarly, so r hat cross theta hat will produce a new vector perpendicular to them. So the perpendicular to r and theta, it's actually phi hat. And dr in this case here equal to r square sine theta d theta d phi dr. Again, we are interested in four physical quantities, which is gradient, in this case psi, it's equal to r hat partial psi partial r plus theta hat over r partial psi partial theta plus phi hat over r sine theta partial psi partial phi. As another quantity is the divergence. So divergence A, in this case here, equal to 1 over r square sine theta partial r square sine theta ar plus partial theta r sine theta a theta plus partial phi r a phi, and again Laplacian psi equal to 1 over r square sine theta partial r square sine theta partial psi partial r plus partial theta sine theta partial psi partial theta plus 1 over sine theta partial 2 psi partial phi square, and the last quantity is the curl A. In spherical coordinates, it's equal to 1 over r square sine theta r hat r theta hat r sine theta phi hat partial r partial theta partial phi ar r a theta r sine theta a phi. Remember, there's no need to memorize all this. It's enough to know that we are interested in gradient, divergence, Laplacian, and curl. Example: find divergence r hat and find curl r hat. Now, to find divergence r hat in this one here, go back to the definition of divergence, which is this one right here. I'll just rewrite it. Now, in our case, we are interested in divergence r hat. If we go back to the original vector A, this one right here, we will see that, again, we are interested in r hat here. We will see that AR, it's equal to 1. So in this one, AR equal to 1. And since we are interested in r hat, no theta hat or phi hat whatsoever, so a theta and a phi equal to zeros. So a theta equal to 0 and a phi equal to 0. Therefore, divergence r equal to, if we see this definition of the divergence, no theta and no, this one here, and no phi, this one here, this part equal to 0, and this part is equal to 0 as well. And AR here, it's equal to 1. So divergence r hat is actually equal to 1 over r square sine theta partial r square sine theta partial r, which equal to 2 over r. Again, if you would like to find curl r hat using the definition of the curl and AR, A theta, and A phi, so it will be equal to r hat, r theta hat, r sine theta phi hat with 1 over r square sine theta. Now, partial r, partial theta, partial phi. Now, AR, it's equal to 1, a theta 0, a phi 0. When you do this determinant, curl r hat will be equal to 0. Now, let's move on to cylindrical coordinate system. If we have here x, y, z coordinates and a point P located here, Now this point P has intercept in the xy plane like this one. So this one like this. And the intercept in the xy plane making angle phi. Now this point P has direct intercept with the z-axis like this one here. Therefore, the point P, this one, has three different axes, which is R, phi, and z. Remember, when you try to draw a cylinder, so you actually have a radius and you create a disk like this one here, and you move this whole disk up in the z direction. So three coordinates we have here, r, and this r sweeps angle phi, this one here, and this one is constant, it's z, similar to the z in the Cartesian coordinates. Now the vector in cylindrical coordinates is defined as A equal to r hat ar phi z plus phi hat a phi r phi z plus k hat, same as Cartesian coordinates, az r phi z. And the differential lengths are dr, r d phi, and dz in such a way dl here equal to r hat dr plus phi hat r d phi plus k hat dz, and the volume element d tau here equal to r dr d phi dz. Again, we are interested in four different physical quantities: gradient, divergence, Laplacian, and curl. So let's have gradient psi in cylindrical coordinates. So psi in this one, it's r phi z equal to r hat partial psi partial r plus phi hat over r partial psi partial phi plus k hat partial psi partial z. Divergence A in cylindrical coordinates, it's equal to 1 over r r plus partial a phi partial phi plus partial azr partial z, like this. Laplacian psi equal to 1 over r partial partial r partial psi partial r plus partial partial phi 1 over r partial psi partial phi plus partial partial z r partial psi partial z. And the last quantity is the curl A in cylindrical coordinates. So 1 over r, you open determinant here, r hat, r phi hat, and this is k hat, partial partial r, partial partial phi, partial partial z, ar, r a phi, A Z. Again, you don't have to remember all these quantities in cylindrical coordinates. It will be given to you whenever you need them. Example, find divergence r hat and curl r hat in cylindrical coordinates. To find divergence r hat in cylindrical coordinates, let's back to the divergence definition and the general vector A definition. I just copied them in this here. Now we would like to find divergence r hat. In this case, AR equal to 1, A phi equal to 0, AZ equal to 0. So AR equal to 1, A phi equal to 0, AZ equal to 0. So from the divergence definition right here, A phi 0 and AZ here 0. So we end up with divergence r hat is equal to 1 over r partial r, and AR, remember it's 1. So the answer will be 1 over r. To find curl r hat, let's create a determinant here, this one here. In cylindrical coordinates, we have r hat, r phi hat, and k hat, partial r, partial phi, partial z. AR equal to 1, A phi 0, AZ 0. You do the math for this determinant, you will find that curl r hat is equal to 0. It's very important to understand how to transform from one coordinate system to another coordinate system depending on the problem itself. Sometimes you want to transform from spherical to Cartesian, Cartesian to spherical, Cartesian to cylindrical, and so on. So let's learn how to transform from spherical to Cartesian coordinates. Back to the spherical coordinates figure, this one right here. Now this is x, y, z, and remember in spherical coordinates we have r, theta, and phi. Now r in this case here, it has intercept with x and y, and it has intercept with z. So r, it's equal to x squared plus y squared plus z squared to the power half. So this is r transformed from spherical to Cartesian coordinates. So we just wrote r in terms of x and y and z. Now if we look at this one here, theta, now this is right angle triangle. Now cosine theta, it's equal to this one here over r, and this one is z. So cosine theta, or theta, equal to cosine inverse z over r, which is, we just calculate this one here, x squared y squared z squared to the power half. Now to identify phi, now we have here intercept with the x-axis like this one. Again, this is right angle triangle, although it doesn't look like 90 degree, but it has to be 90 degree, this one right here. Tan phi, it's equal to y over x. Remember, this is the 90-degree angle, so phi equal to tan inverse y over x. Now we just transform r theta phi into x, y, z coordinates, but we are not done yet because we have also to transform the unit vectors r hat, phi hat, theta hat into I hat, j hat, and k hat. Now, if this is r hat, directed this way here, r hat, it has intercept with the z-axis and it has intercept with the xy plane, like this one here. So r hat equal to, let's name this one a4 here, equal to a4 sine theta, because this one here cosine, and this one here, the image for this one here is sine, plus k hat cosine theta. Now a4 sine theta, this one here, it has x component or intercept with the x-axis here, it's equal to sine theta cosine phi, and it has also intercept with the y-axis, it's sine theta sine phi. So r hat is actually equal to I sine theta cosine phi plus j hat sine theta sine phi plus k cosine theta. Remember, this one here is the intercept with the z-axis. Now, the sine theta comes from the component of r hat xy plane, and the sine here is the component of the r hat in the xy plane. The cosine phi is the intercept with the x-axis, and sine phi is the intercept with the y-axis. So this is r hat. Now, let's find theta hat. Now, this is actually angle theta, and theta hat, remember, when you draw a sphere, you will drag theta hat in this way. Now, if this is a4, let's name it a4 here. If this is theta, this will be theta as well. Now, as we can see from this one here, if this is z hat right here, the negative z hat, so it has component on the z axis here, which is minus k sine theta. Now, it also has a component on the a4 direction, this one here, which is cosine theta. Now, this a4 here has an image exactly in the xy plane this way here, but it's not a4, it's cosine theta. So the new vector here is cosine theta located in the xy plane. Now this one has intercept with the x-axis, if this is phi here, so the x component for this one here will be cosine phi cosine theta, and the y component here will be cosine theta sine phi. After all, theta hat will be equal to I hat cosine phi cosine theta plus j hat sine phi cosine theta minus, because it's negative here, k hat sine theta. Now let's find phi hat in terms of I, j, k. Remember, when you draw a sphere, you first draw the radius, this one here. If this is phi right here, this will be phi hat, which makes 90 degree with this one right here. So if we just make this one right here like this one here, if this is phi, this will be 90 minus phi, and this is 90, so this will be phi. If this is phi, this will be phi. So the y component, this phi angle, the y component for this one here, it's j hat cosine phi, and the x component for this one here, it's minus I sine phi. So phi hat is actually equal to minus I sine phi plus j hat cosine phi. In summary, r hat equal to I sine theta cosine phi plus j hat sine theta sine phi plus k hat cosine theta. Now theta hat, as we can see here, we will see that the derivative of r hat with respect to theta will be theta hat. So this one right here is the derivative of this one right here. And phi hat is actually the derivative of r hat with respect to phi. And remember, phi is not related to theta in any way. Now, let's do the transformation from Cartesian to spherical coordinates. So, if this is the XYZ plane, and this is theta, and this is phi, right here. Now, the x component, if this is r, it has intercept in the xy plane, and with making an angle sine theta, because this is theta, and this will be the new vector, this one r sine theta, and this new vector r sine theta, it has intercept on the x-axis, which is r sine theta cosine phi. So x in this case equal to r sine theta cosine phi. Again, this r here, it has intercept in the xy plane, and the new name for this vector will be r sine theta, and it has intercept on the y-axis, and if this is phi, so it will be r sine theta sine phi. So y equal to r sine theta sine phi. This is pretty simple, this one here. This r has intercept on the z-axis, and z in this case equal to r cosine theta. So we just write down x, y, z in terms of r, theta, and phi. Now we need to write the I hat, j hat, k hat in terms of r hat, theta hat, and phi hat. Previously, we wrote r hat, theta hat, phi hat in terms of I, j, k. I just copied them like in this one here. Now we need to write I hat in terms of r hat, theta hat, and phi hat. Let's do the following. If we dot product both sides of this equation here with I hat, this like this one here, therefore I hat dot r hat equal to sine theta cosine phi, and remember I dot I1, I dot j 0, I dot k 0. Now repeat the same procedure and multiply the second equation, or dot product the second equation with I hat, again, you will get I hat dot theta hat. It will be, in this case, cosine phi cosine theta. And if we dot product the third equation with I, in this case, you will get I hat dot phi hat will be equal to minus sine phi. Therefore, I as a vector can be written as r hat sine theta cosine phi plus theta hat cosine phi cosine theta minus phi hat sine phi. Following the same procedure as we have done here, j hat will be equal to r hat sine theta sine phi plus theta hat cosine theta sine phi plus phi cosine phi. Again, same procedure. To find k hat, it will be equal to r hat cosine theta minus theta hat sine theta. Now, let's learn how to transform from cylindrical to Cartesian coordinates. So if this is x, y, z, remember, to draw a cylinder, you actually draw a radius like this one here, which is parallel to this one here, if this is point P. So r hat will be directed this way right here, and you create a circle, this one here. So if this is phi, and you actually move same way as in the spherical coordinates, so this is 90 degree, and this is phi hat, and you just drag this circle up in the z direction like this one here. So this will be k hat, this one here, and this one will be parallel to the phi hat right here. We would like to transform from cylindrical to Cartesian. Therefore, r in this case, this r here, it has two components because it lies in the xy plane only. So r, it's equal to x squared plus y squared to the power half. And phi, in this case here, if this is phi, so this will be like this one here, and this is 90 degree, this one 90 degree. So tan phi, it's equal to y over x. Phi equal to tan inverse y over x, and z actually the same as z in cylindrical coordinates. Now to find the unit vectors r hat, phi hat, and k from cylindrical to Cartesian, now r hat here, it's equal to, this is r hat right here, it has x component with the x, this is r right here, it has x component with the x, so I cosine phi, and it has y component plus j hat sine phi. Now phi hat, it's the same as spherical coordinates, nothing changed here. It's minus I sine phi plus j cosine phi. Again, k hat is the same as in Cartesian coordinates. Now, if we want to transform from Cartesian to cylindrical coordinates, let's do the following. Now, if this is r, this one here, it has x component, in this case x equal to r cosine phi. Now, it has also a y component, so y equal to r sine phi, and remember no z component here. Now we need to transform the unit vectors from cylindrical to Cartesian coordinates. Let's just copy these. Now we will follow the same procedure we have done in spherical coordinates. So we dot product the whole equation here with I, the whole equation with I, and this one with I. Therefore, when you dot product this whole equation with I, you will get I hat dot R hat equal to cosine phi, and I hat dot phi hat equal to minus sine phi, I hat dot k hat equal to 0. Therefore, I hat equal to R hat cosine phi minus phi hat sine phi. If we follow the same procedure, we can find j hat equal to r sine phi plus phi hat cosine phi, and again k does not change at all. Let's have example. Obtain Laplacian psi in cylindrical coordinates from the Cartesian Laplacian by direct substitution x equal to r cosine phi and y equal to r sine phi. Now let's write down the Laplacian psi in Cartesian coordinates, which equal to partial 2 psi partial x square plus partial 2 psi partial y square plus partial 2 psi partial z square. And we can write down partial 2 psi by partial x square as partial x partial psi partial x, and partial 2 psi partial x square will be equal to partial x times now partial psi partial r partial x plus partial psi partial phi partial x. Now to find partial r by partial x, using the relation r equal to x square y square to the power half, therefore partial r partial x equal to x over r, or r cosine phi by r, which equal to cosine phi. With the aid of the equation tan phi is equal to y over x, we will get secant square partial phi partial x is equal to minus y over x square, or y over r square cosine phi. Now secant square phi partial x equal to minus y secant square phi over r square, and partial phi partial x equal to minus r sine phi over r, which equal to minus sine, this r square over r. Now let's substitute this equation and this equation in this one right here. You will get partial 2 psi partial x square equal to partial x cosine phi partial psi partial r minus sine phi over r partial psi partial phi. Therefore, partial 2 psi partial x square equal to cosine phi partial r minus sine phi over r partial phi times cosine phi partial psi partial r minus sine phi over r partial psi partial phi. After all, partial 2 psi partial x square equal to cosine square phi partial 2 psi partial r square minus sine phi cosine phi over r partial 2 psi partial r partial phi plus sine phi cosine phi over r square partial psi partial phi plus sine square phi over r partial psi partial r minus sine phi cosine phi over r partial 2 psi partial phi partial r plus sine square phi partial 2 psi partial phi square plus cosine phi sine phi over r square partial psi partial phi. And upon simplifying this one here, we will get partial 2 psi partial y square equal to partial y partial psi partial y or partial y partial psi partial r partial y plus partial psi partial theta partial y. Remember, r is equal to x square y square to the power half, and in order to find partial r partial y, so partial r partial y equal to sine phi. We're actually repeating the same procedure as x, so tan phi equal to y over x and partial phi partial y equal to cosine phi over r. Therefore, partial 2 psi partial y square equal to partial y sine phi partial psi partial r plus cosine phi over r partial psi partial phi, which equal to sine phi partial r plus cosine phi over r partial phi times sine phi partial psi partial r plus cosine phi over r partial psi partial phi and partial 2 psi partial y square equal to sine square phi partial 2 psi partial r square plus sine phi cosine phi over r partial 2 psi partial phi partial r minus sine phi cosine phi over r square partial psi partial phi plus cosine phi sine phi over r partial 2 psi partial phi partial r plus cosine square phi over r partial psi partial r plus cosine square phi over r square partial 2 psi partial phi square minus sine phi cosine phi over r square partial psi partial phi in this here. If we add both equations together, partial 2 psi partial x square plus partial 2 psi partial y square, we will get, so this one here, partial 2 psi partial r square plus 1 over r partial psi partial r plus 1 over r square partial 2 psi partial phi square. Now if we add partial 2 psi partial z square to this one right here, you will get Laplacian psi equal to partial 2 psi partial r square plus 1 over r partial psi partial r plus 1 over r square partial 2 psi partial phi square plus partial 2 psi partial z square. The result here is actually the Laplacian in cylindrical coordinates. One of the important equations we use in physics is the Helmholtz equation. Actually, this equation used in waves, in optics, in quantum mechanics, solid state, electrodynamics, and so on. So this Helmholtz equation is defined as Laplacian phi plus k square psi equal to 0. So this equation is called Helmholtz equation. Now to solve this Helmholtz equation, let's learn a technique. It's called separation of variables. Now we will solve this one here in Cartesian coordinates only, and in the advanced course we will solve this in spherical and cylindrical coordinates. So we will solve this one only in Cartesian coordinates using separation of variables. In Cartesian coordinates, Laplacian psi plus k squared psi equal 0, and the Laplacian in Cartesian coordinates is defined as partial 2 psi partial x squared plus partial 2 psi partial y squared plus partial 2 psi partial z squared plus k squared psi equal to 0. Now let's assume that a psi here equal to a function of x, a function of y, and function of z. Therefore, if we substitute this back in this one here, we will get yz d2x by dx squared plus xz d2y by dy squared plus xy d2z by dz squared plus k squared x y z equal to 0. If we divide the whole equation right here by x, y, z, we will get 1 over x d2x by dx squared plus 1 over y d2y by dy squared plus 1 over z d2z by dz squared plus k squared equal to 0. In other words, 1 over x d2x by dx squared plus 1 over y d2y by dy squared plus 1 over z d2z by dz squared equal to minus k squared. And remember, k here is constant. But the good thing here is this part is independent of this and independent of this. Therefore, each part of this equation is equal to constant. So therefore, 1 over x d2x by dx squared equal to minus k1 squared, and 1 over y d2y by dy squared equal to minus k2 squared, and 1 over z d2z by dz squared equal to minus k3 squared. In such a way, k1 squared plus k2 squared plus k3 squared all equal to k squared. And this is called separation of variables because we just separated x from y from z. As an application for this separation of variable in Cartesian coordinates, let's have this example. Now, in this example, an atomic particle is confined inside a rectangular box of sides A, B, and C. The particle is described by wave function psi, in which satisfy the Schrödinger equation, this one right here. Now, what is the smallest value of E for which a solution can obtain? Now, we need to solve this one here using the separation of variables and using the Cartesian coordinates as well. Let's rearrange the equation, this one here. So Laplacian psi plus 2me over h bar square psi, this equal to 0. So if we compare this with the Helmholtz equation, this part here is k squared. We just solved that 1 over x d2x by dx squared equal to minus k1 squared. Now x for this case here, it's equal to sine k1x, or x equal to cosine k1x, and both equations satisfy the solution for this second order differential equation. Now to choose the suitable solution, we will use the boundary conditions. Psi will vanish when x equal to 0, therefore this part will cancel out, and the only solution we will get is this one right here, sine k1x. Now psi also vanishes when x equal a, therefore 0 equal to sine k1 a, and from this one here we can state that k1 a equal to L pi. L is actually some integer, so therefore k1 will be equal to L pi over a. L here again is an integer, and both conditions will be satisfied because sine L pi over a equal to 0 when x equals 0 and x equal to a. Therefore, the solution x will be equal to sine L pi over ax. Following the same procedure, y will be equal to sine n pi over, now b, because it's the other side of the rectangular box, y, and with k2 equal to n pi over b. Again, following the same procedure, z will be equal to sine p pi over c z, with k3 equal to p pi over c. Now remember, psi it's equal to x, y, z, therefore psi will be equal to sine L pi over ax sine n pi over b, y sine p pi over c z. And with the aid of the equation k1 square plus k2 square plus k3 square all equal to k square, we can find that L square pi square over a square plus n square pi square over b square plus p square pi square over c square all equal to 2me over h bar square. Remember, this part here is this one right here. And from this one here, we can state that E equal to pi square h bar square over 2m L square a square plus n square b square plus p square over c square. Now, if we want to have the minimum value of E, set L equal N equal P equal to 1. Therefore, the minimum value of energy for an atomic particle in a box of dimensions A, B, and C will be equal to pi square h bar square over 2m times LNP. It's equal to 1 in order to get the minimum energy. So 1 over A square plus 1 over B square plus 1 over C square. That's it. Thank you for watching.